Swayam Prabha. Digital India. Educated India.
Welcome back to the course Mechanics of Solids. So, in the last lecture we were talking about the analysis of the slender member, and we have seen different force components and the moment components which will be acting in different way in the slender member, right, the axial force, shear force, bending moment and twisting moment. Okay. So, and then we defined the sign convention for the axial force. So, if it is tension then it is positive, if it is compression then it is negative. Then we define the sign convention for the shear force, okay, by following the same sign convention whatever is used for our axial force. So, similar kind of sign convention we proposed for a positive shear force, that means the left part should come down under the action of the shear force. Now, today we will be talking about the sign convention for bending moment, okay, sign convention for bending moment. Now, if you look at say this is my x axis, say this is some exaggerated figure of course, okay. So, even you will see later on, I mean when we will be talking about this bending thing in more detail, you see you will appreciate that the plane section will be remaining plane, okay, even after bending. So, this is some exaggerated figure, after bending this will take some this kind of shape, okay. So, this is my say x axis, say this is my x axis, okay, some exaggerated, it is still horizontal, okay. So, this is some exaggerated figure or whatever, I mean if I try to show like that, this is my slender member, a part of slender member. So, this is my x axis, okay. So, this part, this face is positive, this face is negative, okay, negative x axis, negative x plane, and this is positive x plane. Now, if the bending moment, okay, if it acts like that, as per our definition, this is my positive bending moment, right, because on the positive x direction or on the positive x plane, okay, the moment whatever is acting, that is mxz, is positive in nature, right. Similarly, on the negative x plane, the direction of the moment is positive in nature. So, therefore, this kind of bending moment will give you the positive bending moment. Now, if you look at this shape, basically this top part is your say concave, right. This is something like, if this is the slender member, under the action of bending moment I get this kind of shape, right. The top part is concave and the bottom part is convex. Okay. So, this is nothing but it is defined, it is known as sagging moment, okay. You have the sag, right. So, this is known as sagging moment and this will be defined as positive. Similarly, if you have this kind of say configuration due to the application of moment, okay, that is nothing but the concave is coming now below at the bottom fiber and convexity is coming on the top fiber, right, of the slender member. So, this is nothing but hogging moment, and therefore, as per our definition this will be defined as negative bending moment, okay. So, whenever you get positive bending moment, that will be the, because please try to understand, you need not to remember all those things, because this is pretty convenient to remember that sagging moment is positive, hogging moment is negative, that is very convenient way to remember, but the thing is that it is actually coming from your moment direction. If you have the positive moment on the positive x plane, and the positive moment on the negative x plane, then you will always get this kind of sagging nature of the bending. Similarly, on this plane, if you have this kind of moment, that means on positive x plane negative moment and negative x plane positive, positive moment, if you get, then that ultimately that will give you the negative bending moment, right. So, as per our definition, because see this is this is z direction is say in the normal to the board. So, basically if you consider this moment is always positive, right, in the as per our right hand thumb rule. So, this moment is always positive, right. So, this is coming from the same sign convention. However, to remember it very well, we are introducing some physical interpretation like sagging moment and hogging moment. Okay, fine. So, now if you see that if the plane of loading is only the xy plane, if the, because there in the slender member whatever we have seen in the last class, that we considered all the force components and the moment components in xyz coordinate system, right, all three. Now, but if the loading is in xy plane, which is pretty common, like if you consider a beam, continuous beam, okay, long beam, so only the loading is in the along the xy plane, right. So, in the z direction, that means normal to the beam is very unusual, okay. So, in that situation, right, you have only three components left out to define the nature of slender member, okay. What are those? If xx, that is nothing but the axial force, the shear force F xy, that will be defined as V, and bending moment, that is M x z, that will be called as MB. So, if I consider this is my slender member, okay, this is my say x direction and this is say y. So, therefore, this is your V, this is your F, and this is your MB. So, all components, axial force, shear force and bending moment, all are shown positive on this configuration, okay. So, if the loading is in the xy plane, then only you will be having these three components, the axial force F, the bending moment MB, and the shear force V, that is all, because you will not be getting another shear force component, another bending moment component, or of course, twisting moment is not there, because we are not giving this kind of loading. So, therefore, twisting moment is not there, okay. So, now for most of the times we will be, in this particular chapter we will be considering loading is in xy plane, and we will be trying to solve this kind of slender member, and we will be trying to obtain the unknown axial force, shear force and bending moment, okay. So, now let us take one, before taking one small example, we should know what are the steps involved in this analysis, okay. So, let us do that. Steps involved in this analysis of the slender member. The first one, idealize the actual problem that means FBD all forces etc. Okay. Next step, okay, first you idealize the actual problem. Next step is that using the equations of equilibrium, that you know summation of F is 0, summation of M is 0, okay. Calculate the unknown external forces or support reactions. And the third step, that is the last step, basically cut the member at a section of interest and find the required component by applying equilibrium condition. Okay. Now, what does it mean? So, we will take one small example, simple example, so that you will understand these steps, okay, how they are involved in the analysis process. So, this is a small or simple example problem. This is a beam simply supported like this on this supports. This is a slender member. Of course, I am showing one line, that does not mean it is a kind of line linear. Okay. This is having proper cross section, okay, square or circular, whatever. Okay. Now, one load W is acting here. Okay. Now, the distance from here to here is A, from here to here is B, this support is A, this is B, and the total length of the beam is L. Now, I am taking one section CC at this location, okay, that I will be coming later on, okay, fine. So, this is the problem. So, as per our steps, whatever we just discussed, we have to idealize the system, okay. Once you idealize the system, then basically we will draw the free body diagram. So, if I want to draw the free body diagram, these supports should be replaced by the force reaction force RA and say RB, okay. Only the vertical force will be there, because this is simply supported and there is no horizontal force. So, by using your, and this is your say xy coordinate system, okay, and the loading is in only the xy plane, okay. So, from by exploiting the equilibrium condition, you can get RA and RB, and you know how to do that. So, I am not going to do that thing again. So, by considering the moment equilibrium as well as the force equilibrium, you can find out RA and RB. So, that will be coming as RA as WB by L, whereas RB is equal to WA by L. Okay. Now, as I told you that I am considering one section CC in such a way that it is lying between A and this point. Say if I say this point is say D point, okay. So, it lies between A and D. So, I am considering one section CC which is greater than 0, okay, less than A. And once I draw the section, and then I want to draw the free body diagram of the left side of the section. So, how to look like? So, this is the beam part, RA is acting here, and this is my section CC, okay. So, when I am cutting it, when I am taking it, so this is my second step, if you recall, okay, I am cutting, I mean third step, right, cut the member at a section of interest and find the required component by applying equilibrium condition. So, I am cutting as per my requirement. So, I am cutting now. What is my requirement? I will come to that point later on. So, how I am choosing section CEC. Okay. So, that will be discussed later on. Okay. For the time being, you just believe me that I am taking one section CEC which is between 0 to A, that means between A and D. So, when I am taking this part only, so I should replace the rest of the part by providing some shear force and bending moment, because axial force will not be there. I am not showing the axial force because you do not have any axial force in this direction. So, if there is no force, external force in the x direction, so therefore axial force is 0. That is a very trivial solution, that I am not doing again. Okay. So, now considering equilibrium, you can simply write V plus R A equal to 0. From this I can simply write V equal to minus R A, okay, is nothing but minus W B by L. I can write it, and I can take the moment equilibrium. So, and this distance is nothing but x, because I am choosing one section x distance away from point A. Okay, this distance is x, because I mean my coordinate system is starting from here. Okay, so this is my origin, say. Okay, A is my origin. Generally, we take the left hand side end point as origin. Okay, fine. So, this is x, where x is varying from 0 to A. Fine, there is no issue for that. So, now I will be taking the moment equilibrium. So, moment equilibrium, if I want to take, so MB is there, that is anti-clockwise, and this RA is acting clockwise, RA into x. So, that will be coming as RA into x equal to 0. That is all, because V will not be participating, because I am considering the moment with respect to this section. So, the component or the contribution of V will not be coming into the picture. Okay, fine. So, from this I can simply get MB equal to WB x by L. Okay. Now, you may ask me that why I have taken only the left hand side of section CEC. You may ask me that who has told me to consider the left hand side of section CEC. Now, there is no rule for that. Okay. It is purely based on your convenience. You can choose even the right hand part of the section CEC, and you can check it that the same solution you will be getting. If you consider the right hand part of section CEC, how it will look like? This is my section CEC, this is the beam, here it is RB, okay, and here you have the W, force W, and this distance is not x, L minus x, because x is starting from A, right. So, therefore, this will be L minus x, and if I want to have, because I considered here, I considered shear force as positive, but eventually it comes negative. So, therefore, the direction of shear force whatever I have chosen here, that is wrong, it should be other way around. So, that is different issue. So, we will not think about that thing previously. So, when we will be starting the problem, we will not go by any intuition, we will consider all the things positive or all the things negative as they come, and based on that we can choose our actual direction. Okay. So, here also we will be choosing V as positive. So, if I choose V as positive here, and this is the negative plane. So, V will be positive in this direction and MB will be positive in this direction as per our sagging moment positive. Now, you can check it whether you are getting the same solution of MB and V there or not. You will get it. Okay. So, this is the beauty. So, therefore, whether you consider left hand side of the section CC or right hand side of the section CC, it does not matter, okay, from whether you are coming from A to section CC or you are coming from B to section CC, it does not matter as long as you are consistent with your sign convention and other things, okay, fine. So, now if you look at this problem gives me the shear force. Now, this is the shear force value. Now, this shear force is valid from which point to which point? This shear force is valid from point A to D. Why? Because this section is valid within this zone, within this range 0 to A. So, whatever information I am getting from that particular section, that will be valid only from 0 to A. Now, if I want to go beyond A, that means from D point, from D to B if I want to go, then I have to take one more section. Let us that section is section C prime C prime. That is all. So, whenever what you can conclude from that, whenever you are getting some change in externally applied force, you must take another section to define the whole thing, because from A to D there is no change in externally applied force. Here RA is acting and there is no externally applied force between these 2 points. So, therefore, I have taken only one section and that is defining the whole part. But as long as you reach the point D, immediately you have the externally applied force W here, right. So, therefore, this CC section will not be able to capture the behavior of dB part. So, therefore, I have to take one more section C prime, okay, which will take care of this dB part. Is that clear? Okay. So, now if I take section C prime, so if I take another section C prime as I have shown and consider the free body diagram. So, this C prime section, okay. So, this will be A to L, okay. This is ranging from A to L. So, 0 to A we have got, now A to L, that will completely conclude the whole structure, okay. So, now here we will be taking the right side of section C prime. Why? This is purely based on my convenience, because here you see this is little bit, because the problem is very simple. So, that is why you will not appreciate whether it is difficult or complicated, but here if you see, if you come from right to left, right to section CC, right, that is little bit complicated than if you come from left to right. But here in this case C prime, if you come from left to right, that will be bit complicated than if you come from right to left. Therefore, I am considering right to left. So, this is my L minus x, okay, and this is my MB and this is my V, all I am showing positive, okay. So, here I will be getting RB minus V is equal to 0. So, therefore, V is equal to RB is equal to WA by L, okay, and MB I can find out, you can get it WA by L into L minus x, okay. So, therefore, what you have got? You have got the complete information means the shear force as well as bending moment for the whole beam. Now, at each and every point if you consider on the beam, okay, you will be getting the shear force and bending moment, is not it. So, suppose I am here, what will be my shear force bending moment? I can find out from whatever is there in section CC. If I am here, I still can find out bending moment and shear force by considering section CC. If I am here, I can find out bending moment shear force information from section C prime C prime. So, that means wherever you go on this beam, you can find out the bending moment and shear force information from these calculations. Okay. Now, if you look at these calculations, here V is minus, if you consider CC section, this is the expression for V, this is the expression for MB, okay, and this is the expression for V and MB when you consider section C prime C prime. But if you look at this variation of MB is linear in x, right, with x basically the variation of MB is linear. If you see, this is the mathematical equation, that will be linear. Okay. So, what, and of course, the V, if you see from say 0 to A, it is constant, then again from A to L, it is taking different value. So, now every time if you calculate from these expressions, that may not be that much convenient, or that may not give the clear picture about the variation of bending moment and shear force across the whole slender member. So, therefore, what people do, they try to plot the variation of bending moment and shear force along the whole beam or the slender member, and that variation is known as bending moment diagram and shear force diagram. It is very, very important in mechanics, and if you are going to design something, so this bending moment and shear force diagram will be very, very say prime say information for a particular design engineer, right. So, as an analysis engineer, you have to provide this bending moment and shear force diagram, and based on that the design engineer will decide where the bending moment is coming maximum, where the shear force is coming maximum, and based on that they will try to design the section. Okay. So, in the next lecture we will take this problem again, okay, and we will try to explore the bending moment and shear force diagram and how they look like and what are the informations we are getting from that diagrams. Okay. So, I will stop here today. Thank you very much.